Welcome to week 5 of INST 414, Data Science Techniques. Some announcements for this week. First, on Module 1, we are working on these. There are, I think, 8 in total that have been submitted to the Medium publication and 11 who have been submitted so far. We anticipate getting the grades back as soon as possible. It's just taking additional time for the TA. Note that there is the GitHub repository with some updated code for you here. You are welcome to reuse or build upon any of the code that you see in these repos. So in the Module 1 folder, there are a couple of API examples. One is about the refuge restroom, and the other one is about the aviation API. There are a number of APIs you could use, but you're absolutely welcome to build on these. They show some good examples about how you work with the requests library to connect to a RESTful API and connect or collect data. Regarding Module 2, Module 2 is due this Friday. This module, remember, is about graph analysis. You should be identifying or constructing some graph from data that you have collected, and then you need to identify what it means for a node in your graph to be important. This really is a question about centrality. So in Module 2, we talked about varying centrality metrics from degree centrality to PageRank to betweenness centrality or closeness centrality or eigenvector centrality. What you want to do is select one of those centrality metrics, describe why it works for your question or definition of importance, and then identify or rank some of the nodes in your graph based on their importance. Here in the GitHub repo for the course, the Module 2 folder has some examples for this. So I have one example about using NetworkX directly, a couple examples from social media for Reddit and Twitter collections, and building graphs from them. And then I have the graphs, the O3-graphs notebook, which uses the IMDb data to build a graph of actors who have co-starred with each other. And in the graphs notebook, there are a couple of examples of ranking those accounts or those nodes, those actors, by their different centrality metrics. So you can check that out too. You're welcome to reuse that code as well. This week, we start Module 3, which is about similarity metrics and dimensionality reduction. So the Module 3 assignment is about identifying similarity in content that you're looking for. So in this module assignment that's due on March 11th, so that's a couple of weeks from this Friday, you want to collect some data. Here you can use some pre-existing data. You do not have to collect your own data for this. You can use data from a previous assignment. You can use data from Kaggle, whatever you want. And then what I want you to do is identify some elements in this data set and then look for similar elements. Breaking this down, so as with all of your assignments, you need to work on or identify some non-obvious insight that is used to support some decision, make it actionable. Where did you get this data? And then crucially, what features are you using to define similarity? And which similarity metric did you use? Are you talking about cosine similarity? Are you talking about Euclidean distance? Are you talking about edit distance? Are you talking about Jaccard similarity? Whatever similarity metric you use, you need to specify or identify exactly which similarity metric is useful to you. Then, after you have extracted features for elements in your data set, you have these 3 quote-unquote query entities that I tell you to identify. So if you're in, I have some examples in a second, but if you are looking in the movie data set, you would select 3 different movies and then rank the 10 most similar items to each one of those movies. So critically, you should have 30 different or 30 elements ranked here. That's 10 different items for each of your 3 query elements. Now, nothing says that these 30 elements all have to be different. For example, if you selected the matrix as one of your query entities and ranked the movies most similar to the matrix, you might expect to see the Matrix Revolutions, the Matrix Reloaded, the Matrix Resurrection, and potentially you could select one query movie as the Matrix, one query movie as the Matrix Reloaded, etc. And you'd expect to see some similar sets of movies in your top 10 ranking. But crucially, you should have 3 different sets of top 10. So I want you to show that you're looking at different rankings of elements in this data set. Some examples about what you can do here. So I've already mentioned the ranking movies by similarity based on actor, but you could also do genre or dialogue, color palette if you can featureize color. In social media, you might look at Twitter and rank Twitter users by their similarity in terms of hashtags or domains or people they retweet. Subreddits in Reddit, similarly, you could look at subreddits that are most similar based on the users who post in them as a Jaccard similarity metric. You could look at the domains that are shared in them, the words that are shared across them, a number of different things you could do to rank what subreddits are most similar to r/all, or which subreddits are most similar to r/politics. And you could use like the push shift data to get that data pretty quickly. Or you can look at web pages graphed by graph. You could look for web pages and evaluate similarity across these web pages. So in the Wikipedia case, maybe you look at the language to see which discussion, or you look at the language to see which pages are most similar to which other pages. You check the natural language processing page, which other pages in Wikipedia are likely very similar to the natural language processing page. Or you could use, at the end of module 2, we talked about SimRank. You could use the SimRank metric to identify what are the most similar nodes in the graph, where similarity here is defined as likelihood of landing on that node in a random walk from your source, and rank nodes that way. So you might say, well, what are the most similar pages to the philosophy page, or to the computer science page, or to the information page, and build graphs from the Wikipedia citations there. You could absolutely do that. Or citation networks in the news or in academic articles. Lots of opportunities to do this. It's just a question of what's your data, what are the features in your data, which similarity metric are you going to use. For the selection of your similarity metric, the sklearn library has a number of distance metrics at your disposal. So you can just call the distance metric class and ask for a specific metric, Euclidean distance, Manhattan distance, cosine distance, etc. And it'll give you back a function that lets you calculate similarity between two elements, or two sets of elements, using pairwise, or calculate the pairwise similarity between two sets of elements. This is an easy way to get at these distance metrics. As in the other two modules, there is some code, or I've put some code in the GitHub repository in the module 3 folder, where you can see how I did similarity estimation or similarity-based ranking using movies and their actors in Jaccard similarity. You're welcome to check that out and build on that code as well. That's it for the assignments. For the semester project, feedback for your proposals is available. You're welcome to use this space for any comments or addressing any comments that I have given you to get back all the points that I took off. The point here is to use this as a forcing function to get you to respond and refine your project. I want you to get full points for your proposal. So the proposal revisions are actually worth 0 points, and every point you get back just goes to the offset whatever points I took off in the project proposal. Note that I have set this to be due March 9th, which will be a week from next Friday, because that's the same day your data collection report is due. And it doesn't make a huge amount of sense for your proposal revisions to be due after your data collection report. So you're welcome to get the proposal revisions in sooner than that, but I just want to make sure that whatever revisions are in by the time you submit your data collection report. If you have any issue with that timing, by all means, reach out to me. For your data collection report, recall it's due March 9th. You don't have to have all of your data collected, but you do need to have made progress on collecting your data. How did you obtain it? Make sure that you actually have an API that works for you, or you can scrape data using Beautiful Soup or some of the examples I've shown you, or I've given you in the GitHub repository. You can check those out. I want to know, have you made progress collecting your data? It doesn't have to be all of it, but have you made progress here? How much data have you collected? How many rows is this? How many columns? How many records? How much data on disk, or how big is this on disk? etc. How did you store that? Is it straight JSON? Is it in some database? That's fine for the answer for number 3. How much cleaning did you have to do to this data? That's the answer really, number 4. If you have any questions about this, you can reach out. All right, next point is that several of you have reached out to me with some concerns about the way the class is going. I'll note this is the first time I've taught this course in the iSchool or in an iSchool, and I want to make sure that the class is as useful and valuable and effective for you as possible. So I put together an anonymous survey. It's got 4 questions, essentially: what's working, what's not, what do you want to see more of, and what do you want to see less of. So I have this survey available in the course, and you can take it. It's anonymous. I just want to hear what you all have to say about things that are working or things that aren't working. So over the remainder of the semester, I can plus up the things that are effective and reduce focus on the things that are not effective. So check that out. Also, to address these concerns, I've extended and added some office hours. So I've added some office hours for myself on Mondays from 3:30 to 4:30, and Tanishq, the TA, has extended his office hours from 12:30, from 12 to 12:30 to now 12 o'clock to 1 p.m. On Mondays and Wednesdays. So you can take advantage of that as well. The next thing to talk about as we move into Module 3, I have a couple of exercises that you can look into that provide examples for the material that we'll go over in Module 3. So first, and you'll see this in the GitHub repository I've already talked about, finding similar movies. And the second one is about using min hashes and similarity and reduced feature space, which we'll talk about in this lecture today. The first exercise, as I mentioned, is about finding similar movies. So the idea is, given some set of movies and the actors who've played in them, or the genres of these movies, select a particular movie from your data set. Could be any movie that you want: Matrix, Star Wars, any movie that exists in this data set. And what I want you to do is find the 10 most similar movies using Jacquard similarity. We'll talk about what Jacquard similarity is in the lecture. It's essentially a way to measure the overlap between 2 sets of things. So it's a score that tells you how similar 2 sets of things are. And what I want you to do is use that to find the most similar movies based on the actors who star in them from your selected movie from the data set. The second exercise is to push on the large size of the IMDb movie data set. So you'll note when you do the Jacquard similarity piece, if you were to treat this as a data frame, you might have, I think it's something like several 100,000 columns in the data frame, one for each actor, which is difficult to scale. When we talk about the lecture today about min hashes, I'll show you how you can use hashing to reduce the number of columns down for this data set from whatever the 100-some-odd-thousand is to, say, 10 or 20 or 128, and still be able to estimate the Jacquard similarity between 2 elements in this reduced space. So here in this exercise, what I want you to do is try and build that min hash signature for the data in this movies data set. And I have examples for how you do this in the GitHub repository. So you can increase the size of or the number of hash functions here and see how that changes your estimate about similarity and increases or decreases your performance. Because if you construct a min hash signature with only 10 hash functions, it's going to be much smaller data than the full data set if you were treating it as a data frame. And as you increase the number of hash functions, what you'll see is you should get better estimates of Jacquard similarity at the expense of more space. So you can explore this here because it will play a role when we talk about locality sensitive hashing at the end of this week and beginning of next week. As I mentioned, the min hash exercise also has an existing sample in the course GitHub repository that you can check out. All right, what are we going to talk about this week? So the first part of Module 3 has 4 main learning objectives. The first, we want to focus on distance metrics. So last time and at the end of Module 2, we talked about identifying similarity in a graph using SEMRank. And in the next module, when we talk about unsupervised learning and clustering, we want to be able to evaluate how similar two objects or elements in your data set are, because that's going to be the foundation for how we build clusters. We want two elements in the same cluster to be close or have a small distance, two elements in different clusters to be far or have a high distance between them. So there are many different ways to evaluate distance, as there were many different ways to evaluate centrality in the graph examples from last time. The next thing we'll talk about is applying something called shingling to text. So when we talk about movies and actors, we can very easily say this movie has this set of actors in them. But when we talk about documents, how do we featureize these documents? One way is called the bag of words method, which is a popular way. Another way is called shingling, where you slide essentially a window over the letters in your data set, or letters in your article, or letters in your document, and use the window of letters as your essentially set of words. And this allows you to have a defined and bounded set of vocabulary, whereas if you were just using bag of words, this might be an unbounded set. So we'll talk about this as a way to create features for documents in a way that is not as clear as features for movies or features for graphs. Then what I want to do is talk about the relationship between Jaccard similarity, which is one of the major similarity metrics we use when we're trying to evaluate similarity between sets, and the min-hash. The min-hash approach is a way, as I mentioned in the exercise a second ago, is a way to calculate or estimate Jaccard similarity without having to store the full set of features for a particular piece of data. And then I want to explain the intuition behind locality-sensitive hashing. So why am I having you explore these bottom 2 points? The main thing here is when we look at large-scale data sets, we're talking about like web-scale large data sets, sometimes this can be so large that they don't fit in memory. I'll talk about an example about this when we talk about distance matrices. There's a similar kind of problem that we saw with the frequent item sets exercise, where if you want to count up all pairs of elements in a data set, that can take a very large amount of memory, and we want to be able to do that without having to store or evaluate the full set of data, or all sets or all pairs of data. So we talk about clustering. This is particularly useful or particularly important because if we are having to store the full distance matrix to figure out the clusters, this can be problematic in terms of memory that we use. And you could actually easily outrun or overrun your memory with something even like the IMDb data set that you have in your exercises. So these bottom 2 things are about how we deal with, or the kinds of methods we can use to deal with these large scale data sets. It's not critical that you understand like the ins and outs and the details of how we construct min-hashes or locality sensitive hashing, but I do want to give you some intuition about how these processes work. So when you encounter very large data sets, or even slightly large data sets, and you want to do some kind of sophisticated analysis on them, you have an idea about how you might do that without having to, in the case for locality sensitive hashing, how you might build a data structure that lets you identify candidate pairs of elements that are likely similar to each other without having to evaluate similarity across all possible pairs of elements. So that's really the goal there. The first element, the first objective about distance metrics is going to be the most useful to you. Shingling is going to be valuable for featurizing documents. And these bottom 2 pieces about min-hashing and locality sensitive hashing are primarily about scalability things. So I want you to get some intuition for how those work. Then for next week, I want you to read up on Chapter 11, Sections 11.1 and 11.2 and 11.3, which are methods for doing dimensionality reduction. We'll talk about min-hash as one method for dimensionality reduction, but I'll show you a couple other methods here I won't go deeply into the math behind them. I'll show you the code, some code in Python for how to deal with these methods or how to use these methods for doing dimensionality reduction, which will be useful for next module when we talk about clustering. Otherwise, remember that Module 2 is due this Friday. Your revisions need to be submitted by the 9th, so you get those in. And if you have any questions, feel free to post in the discussion forums, come to my extended office hours or Tanish's office hours, or feel free to send an email.